I don't have your tests, first of all. I'll have those on Monday, though. So today we're going to do just kind of like a one-day deep dive into the math of principal stresses. So you sort of see how it all works. And then after we do that, we're not really going to use that anymore in this class, but eigenvalues and eigenvectors are going to be an important thing to understand in pretty much all your classes from here on. So I thought it made sense to talk about it a little bit. Okay, so this is like the mathematical understanding of eigenvalues and eigenvectors. Okay, and so this is the basic idea. This is what we're trying to do when we derive this idea of eigenvalues and eigenvectors. So given a matrix, and well, specifically a stress tensor for us, and I'm going to call it sigma, and we're going to make it symmetric. So it's xx, xy, xz, then xy again, yy, yz, then xz again, then yz again, and then zz. How can we find coordinate axes for which all stresses are normal stresses? Okay, so as a first hint about how to do this, to think about how to do this, so say that this principal stresses idea hadn't been invented yet, how would you think of this stuff? Think of trying to find one face where the stress component is perpendicular to the face. Component isn't really the right word. Where the stress is perpendicular to the face. So what have we done that lets you answer a question like this?
What you multiply it by a normal vector, 1, 0, 0.
Yeah, except that we don't know that it. That's right. We don't know that it's going to be one of our. So starting with this stress tensor, we don't know that it's going to be one of our coordinate axes. We just know that somewhere out there, there's going to be a face where the stress is going to point exactly straight out of that face. So do you remember a topic that we did that relates to calculating stress components on that face? Tractions, remember talking about tractions? We didn't spend a lot of time on it. So what we want to find is a face where the traction is perpendicular. And remember how we found tractions? Remember that the traction was equal to the stress tensor times some nx, ny, and z. And this was an outward facing normal. To the face. Okay. And now so this is how we're going to calculate the traction on a given face. Okay. And how are we going to specify that that traction is fully perpendicular to the face? So we want to specify, we want to require that this traction vector is perpendicular to the face. And the way we can do that is we can say, so we're going to require that the stress tensor times this outward facing normal is equal to some constant that I'm going to call lambda times that outward facing normal. So this is the traction on a face. And this is the part where we're requiring that the traction is entirely perpendicular, entirely parallel to the outward facing normal. Okay, so sit and think about that for a second. So this is the origin of the principal stresses. We're trying to find we're trying to find a face, and this face is defined by its outward facing normal. Okay. And we're trying to find a face where the traction is entirely parallel to that outward facing normal. Okay. You're not leaving until someone says something inspiring about this. No, I don't know what I'm expecting you to say, but this is the idea. So how are we going to solve this? So, yeah.
Is the sensor going to be equal to that?
Is what?
The sensor going to be equal to that?
Well, the stress tensor is a matrix, okay? And when you multiply the stress tensor in general by an outward facing normal to a face, you end up with 3 components of traction, okay? But for this special kind of thing, you calculate the traction for a face, and the traction that you get is just straight out of the face. It's parallel to that outward facing normal. So that's what we're requiring. That's in general, that's not the way it works. But when you get to a face corresponding to a principal coordinate system, this is what happens. So we're just trying to identify those. Okay.
Is there like a real life example of traction? Like, how is it like? Like an example?
Well, like for example, I mean, I guess I would just think of attraction as like related to changing coordinate systems for a state of stress. You know, it's just you're just choosing the orientation of your coordinate system and seeing how the stress changes as you do that. That's what attraction is about. Um, Okay, yeah.
Is it normal or what's the end again?
Okay, well, that is the outward facing normal for the face that we're looking at.
Okay, so then the outward facing normal on both sides of that equation are the same numbers, correct? Or are they different?
Okay, so lambda then is the eigenvalue, which in this case is the principal stress. N, X, N, Y, and Z is the eigenvector. And this is a corresponding eigenvector. Remember, a single eigenvalue and a single eigenvector are always connected. And so this is the corresponding principal axis. Okay, and so it just comes down to a mathematical question of enforcing this equation. Okay, so now the mathematical question is just how are we going to enforce this equation? Notice a couple things. So two things. So the first one is the eigenvector is always, it can be plus or minus. Okay, it doesn't matter whether you, like if you multiply an eigenvector by -1, you still get an eigenvector. Okay. So negative nx, negative ny, negative nz is also a corresponding eigenvector. And the second thing is any number times the eigenvector is also an eigenvector. And you can see all that from this equation. You can see both of these. So say that we found a lambda that works along with an nx, ny, and z that work. Okay. Multiply nx, ny, and z by -1. Okay. You also have multiplied this one by -1 because these are the same thing. You can pull those negatives out of the equation, divide both sides by -1, and you haven't changed it at all. So that's why it's always plus or minus. You can use the positive ones or the negative ones. It's the same. Okay. Same thing works with any constant. Like imagine that you find a lambda and nx, ny, and z. And now multiply the eigenvector by 5. Well, you've also multiplied this one by 5. You can pull the 5s out of the equation, divide both sides by 5, and you haven't changed anything. Okay. So when we do eigenvectors, I tend to use unit vectors because why not, you know? But you could multiply that by 100, by 1,000, by 1,000,000, by 2.5, by pi. any constant that you multiply, it also works this way. Okay, so now let's see what this equation gives us. So now we're going to try to find the eigenvalue and the eigenvector so we're going to start with this. Sigma xx, xy, xz, xy, yy, yz, xz, yz, zz, and we're going to multiply it by nx, ny, and z. And we're going to set that equal to a number, lambda, times nx, ny, and z. And another way to write this is to multiply it by the identity matrix, which is all ones on the diagonal and then zeros. So this is easy to confirm that this is the same. I'm going to rewrite this as lambda 0, 0, 0, lambda 0, 0, 0, lambda times nx, ny, and z. If you multiply that matrix out, you get the same thing as just this number lambda times the vector. And now we can subtract that matrix on the right side of the equation from both sides, and we get this. Sigma xx minus lambda for the first element, sigma xy, sigma xz, sigma xy. Then here we have sigma yy minus lambda, sigma yz. Then here we have sigma xz, sigma yz, and sigma zz minus lambda. And we're multiplying that by this. And this now has to be equal to 0. Okay, so I just did some simple matrix algebra to rewrite it in this new form. And for nx, ny, nz, to give an answer that's not just the 0 vector, we need this matrix to be non-invertible, because if you can multiply it by its inverse, you just get an answer of zeros. Okay, so we need this matrix to be non-invertible. And that requires that the determinant is equal to 0. Okay? So now we've simplified this problem. Like, let's keep track of where we are. We've simplified this problem of requiring that sigma xx minus lambda, sigma xy, sigma xz, sigma xy, sigma yy minus lambda, sigma yz, sigma xz, sigma yz, and then sigma zz minus lambda. Determinant, that's what this means with the, like the absolute value of this thing, is equal to 0. Okay, so that's our task now. We know that we've solved this problem if we can come up with a way that this determinant is equal to 0. So how would you calculate that determinant? I'll write this out. You don't really need this in your notes, I suppose, but I'm going to write it as, so it's going to be, how many of you have done determinants in classes before? So yeah, it's going to be, we can think of it as this top left number times the determinant of this submatrix minus sigma xy times the determinant of a submatrix plus sigma xz times the determinant of this submatrix. And so it comes out to be this sort of ugly thing, but it's so sigma xx minus lambda times the quantity sigma yy minus lambda times the quantity sigma zz minus lambda minus sigma yz squared. And then minus sigma xy times sigma xy times the quantity sigma zz minus lambda minus sigma xz times sigma yz. And then plus sigma xz times sigma xy times sigma yz minus sigma xz times the quantity sigma yy minus lambda. And we have to set this equal to 0. And look at the orders of the things that we're multiplying together. Each one of these terms is going to be a cubic. You see that? And so this requires solving a cubic equation for lambda. And that cubic is going to give 3 answers. And those are the 3 principal stresses. Okay, well, solving a cubic polynomial is hard. You know, there's no formula for solving a cubic, but there is a quadratic formula if it happens to be able to reduce to a quadratic equation. And so if one of those eigenvalue answers, one of those roots of that cubic polynomial is 0, then it turns out we can just use the quadratic formula for the other two. And so that's a way for certain problems where you happen to have one principal stress that's zero, this can be solved easily by hand. Okay, so cubic polynomials are hard to solve. I mean, not that hard to solve, but there's just no formula for it, no systematic way to do it. But if one root is zero, what's left is a quadratic formula or a quadratic equation. And that's easy. Okay, so let's just go through a problem. So I'm going to do an example like that. Okay, so here is the example. I'm just going to give you a stress tensor that I happen to know has one principal stress of zero, and we're just going to solve this by hand. Okay. So let's say that my stress tensor that I'm starting with is 6.25, negative 6.5, 0, negative 6.5, negative 1.25, 0, 0, 0, 0. And we're going to find the principal stresses and the corresponding eigenvectors. Okay. Well, after we go through that little bit of matrix algebra, remember we just come up with a problem of setting a determinant equal to zero. So here is the matrix where we're trying to set the determinant equal to zero. Okay, so we want to set that determinant equal to zero. And if I multiply this out, calculate this determinant, I got 6.25 minus lambda times negative 1.25 minus lambda times negative lambda. And then we have minus 6.5 times 0 minus 0. So that one goes away. And then we have plus 0 times 0. So that one goes away. And all we're left with nope. Sorry, I made a mistake here. On the second one, we have 6.5 times So this should be minus negative 6.5 times negative 6.5 times negative lambda. And then the last one is 0. And if you multiply this all out, you can pull a negative lambda out. And you have this times the quantity 6.25 minus lambda times the quantity negative 1.25 minus lambda minus 42.25 is equal to 0.
So one of the values would be just lambda equal to 0.
Exactly. So that's what we needed to turn this into a quadratic equation. And if you multiply this out and simplify it, you end up with, so we have that negative lambda, and then on the inside, we have lambda squared minus 5 lambda minus 50.06. And so the roots to this are lambda is equal to 0, lambda is equal to negative 5, and lambda is equal to 10.
Or just like running down to 0.06 then in this example.
I guess that's right. Yeah, probably. There's some round off in here. Yeah. Okay, so now we've found the principal stresses. Those are the 3 principal stresses. Okay, and that includes the maximum possible normal stress, the minimum possible normal stress, and then one in between. And now we're going to go about finding the corresponding eigenvectors. Okay. So now we're going to find the eigenvectors corresponding to each lambda. So first I'll do it for lambda equals 0. Okay. Well, what we want, I'm going to go back to this form of the equation. I'll put it in red here. This is the one I'm going to keep coming back to. And I'm going to plug 0 in for lambda. And then I'm going to solve for nx, ny, and z. Okay? So I'm going to plug 0 in for lambda. So this matrix becomes 6.25 minus 0, negative 6.50, 0, negative 6.50, negative 1.25 minus 0, 0, 0, 0, and then 0 minus 0. And we're going to multiply, we're going to find an nx, an ny, and an nz that makes this equal to the 0 vector. So that's what we're looking for. So notice that we're going to find an nx, ny, and nz that's specific for one of those roots, for lambda is equal to 0, okay? Because we've plugged in 0 for lambda in that equation I just circled. Okay, so what does this look like now? So we have 6.25, negative 6.5, 0, negative 6.5, negative 1.25, 0, 0, 0, 0. And we're multiplying it by nx, ny, nz, and requiring that it comes out to be 0. And so this gives you the equation 6.25 nx minus 6.5 ny is equal to 0. Then the second equation says negative 6.5 nx minus 1.25 ny is equal to 0. And the third one says 0 equals 0, so that doesn't help.
Is there any way we can just use the inverse matrix to find the normal vector? I don't think that works in this case, right?
Right. Well, remember the way we set this problem up is these are the three cases where there's no inverse for this specifically. That was what we required. So yeah, we can't do that. So what do these tell us? So the first, so these two tell us that nx is equal to 1.04 ny. And the second one says nx is equal to negative 0.192 ny. So what values of nx and ny make this possible? Yeah, that's right. So nx and ny both have to be equal to 0, which means that this eigenvector is parallel to the z-axis, okay? And it can be plus or minus, and it can be any length. We're going to make it a length of 1. And so our first eigenvector, our E vector, and I'll say a unit E vector corresponding to lambda equals 0 is plus or minus 0, 0, 1. Okay. Now we're going to do the same thing with the next one. What are the two? Negative 5. So let's do negative 5. So now lambda is equal to, this is the next one. And we're going to do lambda is equal to negative 5. So we have 6.25 minus negative 5, negative 6.5, 0, negative 6.5, negative 1.25 minus negative 5, 0, 0, 0, 0 minus negative 5, times nx, ny, and z is equal to zeros. And so this says 11.25, negative 6.5, 0, negative 6.5, positive 3.75, 0, 0, 0, 5, times nx, ny, and z is equal to the 0 vector. Okay, so take a couple minutes and see if you can figure out a unit vector nx, ny, nz that solves this. Go through it.
I got an answer. It was 0.87.50.
Yeah, that's what it is. Yep. So let's do it. So we got 11.25 nx minus 6.5 ny is equal to 0. And then the second one says negative 6.5 nx plus 3.75 ny is equal to 0. And the third one says 5nz is equal to 0. Well, this one tells us that nz has to be 0. There's no way around that. And those other two, it turns out, are redundant. One's a linear multiple of the other one. So to see that, so we have from the first one, 11.25 nx is equal to 6.5 ny. I'll plug in, and if this second one, you could see it gives the same thing. So 6.5 nx is equal to 3.75 ny. Both of these two together just tell you that oh, 6.5. In both cases, it just tells you that nx is equal to 0.57 repeating times ny. And so I'm going to plug in 1 for ny. And what I'm going to get out is that nx, ny, and z is equal to 0.57 repeating, 1, 0. Now normalize it because we want it, it's a little easier to use as a unit vector. Normandale. Normalize it. And so a unit vector in that direction is, so this unit vector is 0.5, 0.8660. And this is plus or minus, and that's your eigenvector corresponding to the eigenvalue of negative 5.
How do you normalize it again?
Divide by the magnitude.
Oh.
Okay, last one. So this is lambda equal to, what was it, positive or negative tan positive? So take a few minutes and see if you can work through this one from here. I'll never make you do this again.
Could you scroll out a little bit? Thanks.
So we have 6.25 minus 10, negative 6.5, 0, negative 6.5, negative 1.25 minus 10, 0, and then 0, 0, and then 0 minus 10. And so that gives negative 3.75 nx minus 6.5 ny is equal to 0. And then we have negative 6.5 nx minus 11.25 ny equals 0. And then negative 10 nz is equal to 0. So this one right away says nz is 0. These two each say the same thing, that nx is equal to 6.5, 3.75, 1.73 repeating ny negative. So if you set ny equal to 1, then nx, ny, nz is equal to negative 1.73 repeating, 1, 0.
You said ny negative 4.
I chose it to be 1.
Oh,
You can choose, but the relationship that we have is whatever you choose for ny, nx is negative 1.73 times that. And so as a unit vector, then, if you normalize this, you get negative 0.866, 0.5, 0, and this is plus or minus. Well, notice you never have to compute the last one this way. I mean, I wanted you to go through it once, but since they're all perpendicular, once you have the first two, you can just take the cross product of both of those, and that'll give you the third one. So really just calculate the first two this way. And then cross them for the third. Okay, so if you ever get confused about like what the eigenvector means corresponding to the eigenvalue or whatever, all that information is here. It takes a while until you comfortably wrap your head around it all, I think. It'll make sense, but then you'll sort of forget whatever. But this is something that's just going to keep coming up in classes over and over again. And if you can remind yourself that what we're doing here is we're trying to find an outward-facing normal to a face, where when we calculate that traction, we don't have any shear elements in that traction. The traction is parallel to that outward-facing normal. Okay, and the rest we're just reasoning through mathematically, and they have to be mutually orthogonal. Okay, that was a lot. Let's stop. And then, so basically from now on, we're going to go back to pretty nuts and bolts type uses of of principal stresses and stuff. But if you ever want a deeper understanding of what's going on, you can go back to this and just little by little wrap your head around it,